Welcome to lecture 4 of the course. In the last lecture we saw a brief review of what is non-deterministic Turing machine and the classes n time Tn, followed by some example problems, and then we defined NP. Then we saw some example problems in NP, followed by a brief description of the P versus NP problem, right, which is a big open problem in computer science. So today we will see some more, one more example or one more canonical example of a problem in NP, followed by another characterization of NP. Right, so we realized or we learned that NP is a class of all languages that can be decided by non-deterministic polynomial time Turing machines. So today we will see another characterization for that. Okay. So first let me define what is called SAT, the problem called SAT. Right, it's SAT is short for the satisfiability, the word satisfiability, or sometimes it's also called as a Boolean satisfiability problem. Right, so you are given a Boolean formula, say maybe you are given something like this, x1 or x2, x1 and x2, x2 or x3. So these kind of things that kind of look like an inverted V are called wedges, and they stand for AND, the Boolean and the ones that look like a V are called stand for the Boolean OR. Okay, so now these are Boolean variables x1, x2, x3, x4, and now you are asking, so what is satisfiability problem? Given a formula like this, now is there any way to assign values, true false values to x1, x2, x3, x4 such that this formula evaluates to true? So let us see. So in this formula, is there any such way? So now this is an AND of 4 things, x1 and x2 or x3 and x3 complement, this bar at the top means complement, and x3 or x4. So these 4 things need to be true. So this means that x1 has to be true, and this means that and it's an AND of 4 things, so all these 4 things must be true. So this means that x3 also must be false, because x3 complement must be true, right? And now because x1 must be true and x3 complement must be true, okay, so we got the inference that x3 must be false. Now since x3 must be false, now look at the last part, so which says x3 or x4. So now x3 has to be false, but so x4 has to be true for this part to be true, right? So x4 has to be true, and likewise x2 also has to be true. So one way to satisfy this Boolean formula is for x1, x2, x4 to be true and x3 to be false. And it looks like this is the only way for this Boolean formula to be satisfied. However, it doesn't matter whether it is the only way or if it's one among many ways. The point is that there is one way for it to be satisfied, right? So again, just to formally define, it consists of Boolean formula, consists of Boolean variables like xi, negated variables, which is the complement denoted by xi with a bar above it, and sometimes both xi and xi complement are together called literals. Okay, so both are two different forms of xi, and they are connected by AND and OR. So AND is denoted by an inverted V and OR is denoted by a V, and of course they are also categorized or organized with parentheses. And formally, SAT is a collection of, or is a set of all Boolean formula such that they are satisfiable, meaning there is some way to assign the variables in there in such a way that the Boolean formula evaluates it true. So this Boolean formula that I have written over here, right, this one, it is satisfiable. This is in SAT, right, because we found a way of assigning true false values such that this entire formula evaluates to true. Right, so satisfiable means there is an assignment of true false to the Boolean variable such that the whole formula evaluates to true. Now some minor examples or some special subclasses of the SAT. Okay, SAT is the class of all Boolean formulas such that are satisfiable. Now we will learn something called conjunctive normal form. So conjunctive normal form means it is an AND of ORs. Okay, so what you will have here is an AND of clauses. The whole formula will be an AND of clauses. So something like this, let's say the whole formula phi. Okay, phi is just one way to like we call a variable in algebra as x, right? So like that a Boolean formula is sometimes called phi, right? There are also other notations like psi, right? So phi is C1 and C2 and so on till Cm. That is an AND of m clauses where each clause is of the form, right? Ci is of the form something, some xi1 and or not and or xi2. Sometimes some of them would be complemented, something like this, right? So what we have here above in the blue is a conjunctive normal form because we have three clauses, right? So the whole formula is an AND of three clauses and each clause is an OR of literals, right? So this is why it is a conjunctive normal form. So each clause is an OR of literals, which is what is happening here. In fact, even the first formula that we talked about here, this formula that we said is in SAT, even that is of the CNF form, a conjunctive normal form, right? Because it's an AND of four clauses. The first clause turns out to be has just one variable, so it is trivially an OR of variables. So second clause has two variables or two literals, third clause has one literal, and fourth clause has two literals, right? So CNF SAT, right? So CNF form is this form where you have an AND of clauses and each clause is an OR of literals. So CNF SAT is a subclass of satisfiability consisting of all Boolean formulas in the CNF form which are satisfiable. Again, this big formula over here is certainly satisfiable. You can see there are too many variables x1, x2, x3, x4, x5, x6 and just three clauses to be satisfied. So you can easily figure out ways to just x1 is true and x2 is true and x3 is false, for instance, satisfies this, right? CNF SAT is a class of all Boolean formulas in CNF form that are satisfiable. You can also write CNF forms that are not satisfiable, right? So in fact, if you had here in the first formula over here, if you had AND of, let's say, if you had another clause over here and let's say x4 complement or x2 complement. Now this, if you take all these five clauses together, it cannot be satisfied simply because we already learned that with the four clauses to be satisfied, x2 and x4 have to be both true. Now once x2 and x4 has to be both true, in the last clause x4 and x2 have to be both false to make the last clause true. So this is an example of a Boolean formula that is not satisfiable, a CNF Boolean formula that is not satisfiable. And another subclass of CNF SAT is what is called 3 CNF SAT, right? Where it is of the CNF form, something like this. But in addition to it being on the CNF form, in the CNF form, we are also insisting that each clause has exactly 3 literals. So here the first clause has 4, second clause has 3 and the third clause has 2. But 3 CNF SAT or 3 SAT for short, we want each clause, it should be in the CNF form, right? and each clause should have exactly 3 literals, and the formula has to be satisfiable. And interestingly, perhaps not so difficult for you to see at this point, all the 3 languages, SAT, set of all satisfiable Boolean formulas, 3SAT, or CNF SAT, the set of CNF formulas that are satisfiable, and 3SAT, which is a set of 3 CNF formulas that are satisfiable, they are all in NP. How it's not so hard to see. You could have a non-deterministic Turing machine first. You could have a non-deterministic Turing machine like this. First, decide x1 to be true. Like, what should x1 be? Should x1 be set to true, or x1 should be set to false? Right? Basically, it is non-deterministically choosing whether each variable has to be true or false. Right? And after x1's true false status has been chosen, then you decide whether x2 has to be true or false, and so on. So when the tree, let's say there are n variables, after n levels, you would have 2 power n leaves. At each leaf would correspond to a certain assignment. Like, there could be a leaf where all the variables are true, there could be a leaf where all the variables are false, there could be a leaf where x1 is true, x2 is false, x3 is false, x4 is, whatever order or whatever way you want it, all these assignments will appear as each leaf. And right, so this is the non-deterministic part, where we non-deterministically choose the variables, the true false assignment for each of these variables, and then all that you have to do is evaluate the formula at this assignment. So given a certain assignment, one has to evaluate the formula. This could be done by a simple algorithm in polynomial time, in deterministic polynomial time, right? So once I tell you x1 is true, x2 is false, etc., like in this formula, for instance, x1 is true, x2 is false, x3 is true, something, then it is very easy for one to evaluate whether for this assignment does this formula evaluate to for this assignment does this formula evaluate to true. So the non-deterministic part guesses, or non-deterministically guesses all the possible assignments, and if any assignment leads this makes this formula true, then you will find it in the 2 power n choices. If this formula is not satisfiable, right, all whatever assignment you assign, like in this case, this particular case, whatever assignment you assign, none of these assignments are going to satisfy it, because whatever you assign, there will be some clause or the other which is not true. So in which case this whole evaluation will all the paths will lead to a reject. Whereas if there is some satisfying assignment, then the path corresponding to that satisfying assignment will lead to an accept. So the formula will be accepted because it has at least one accepting computation path. Hence, again, the whole whatever I described works whether it's a Boolean formula, it's a specific Boolean formula like CNF formula, or a 3 CNF formula, right? So they are all in NP, right? So one thing that you may want to observe here is that we saw 3 colorable, we saw satisfiability, we saw subset sum. In each of these cases, we kind of non-deterministically choose a solution and then verify that this solution is a valid solution, right? So there is an initial part which is non-deterministically choosing something, or one might say guessing something, right? And then followed by verifying whether this guess that we made is a valid solution. So now one might wonder, like, so is it just a coincidence that these three computational problems, they are in NP because of a certain type of solution? First you guess and then you verify. Or is it that every problem in NP has a guess and verify solution, right? So that is one question, and the answer turns out to be yes. Any problem in NP has a guess and verify solution, right? So this I alluded to this in the previous lecture as well. So we'll see the proof of that. So first, let us formalize this notion of guessing and verifying. So a verifier, so first let me define a verifier. Okay. Once again, I just want to say there is a guessing part which is not deterministically guessing something or not deterministically choosing something, followed by a verifying part which is completely deterministic. There is no not determinism going on, right? So a verifier is we are trying to model this latter part, the verification part. So a verifier is a decider or a deterministic decider, or you can think of it as an algorithm, a deterministic algorithm, such that a verifier for a language is a deterministic algorithm or a deterministic Turing machine, such that for all the members of the language X, right, there is some Y that the verifier can verify, that can use to verify that X is in the language. In other words, if X is part of the language, so for instance, maybe it's easier explained with an example. So now consider this graph. Now, is it a 3 colorable graph, right? So the problem, the language is the class of all 3 colorable graphs. So maybe I'll just erase this. And now you are trying to determine whether this graph is 3 colorable. So one way to do it is to guess a coloring assignment. So maybe you guess red, red, green, green, blue. And the verifier simply checks whether this coloring assignment is a proper coloring. Of course, the answer is no, because this edge has 2 reds on either side. This edge has 2 greens on either side. But if you consider another assignment, red, green, blue, maybe red over here, this corresponds to a valid 3 coloring. And so now, is this graph 3 colorable? Yes. Now, if I give you this 3 coloring, the verifier can verify that this is an actual 3 coloring, right, as a proper 3 coloring. So with the help of this assignment, a verifier can verify that this graph is 3 colorable, right? So I want to decide, or I want to verify whether this graph is 3 colorable. Sure, you can do that, because if I give you the 3 coloring, you can verify it, right? So whenever X is in L, there should exist a Y. Okay, Y is the information that we need to supply to the verifier, right? And sometimes it's called proof, sometimes it's called witness, sometimes it's called certificate. So you can think of it, right? Now I want to say that this graph is 3 colorable. Now how do I convince you that this is 3 colorable? So now you are asking me, okay, give me a certificate or give me a proof that this is indeed 3 colorable. So now I'll tell you, okay, now look at this particular 3 coloring. It's a valid 3 coloring for this graph. Now once you get the valid 3 coloring, you can verify, okay, this edge is fine, this edge is fine, this edge is fine, and so on. And then you are convinced. So that's why it's called a proof or a witness or a certificate. Okay, it's a witness to the fact that it is 3 colorable, such that we can use this Y, right, to verify that X is in the language. In the case of a subset sum, I would give you the subset that sums to the target T. Now suppose this graph was not 3 colorable, right? Now that means whatever way you assign 3 colors, it is not going to be a proper coloring. So there is no way. So this graph is this. You cannot produce a certificate for this to be part of the 3 coloring. Right? Whatever certificate you give, it will not be verifiable, because the verifier cannot clear it. So all that we need is one certificate, right? Sometimes there could be multiple certificates, right? So now if I change, for instance, if I change, not much scope for any changes here. So maybe, I don't know, maybe Yeah, in this case there's not much scope for changing much, but we could do something like this. Let's say this is blue, this is green, and this is blue, right? So this is different from the, so there are multiple certificates, right? This is different from the earlier coloring. So it doesn't need multiple certificates, but there should be at least one certificate for, so if X is in the language, there should be some certificate Y such that we should be able to verify that X is in the language with the help of Y. And Y is called proof or witness or a certificate. Right? And again, I said this in the previous lecture, verifying the certificate is something seemingly simpler than deciding whether the X is in the language or not, right? So testing whether X is in the language is seemingly harder than verifying whether Y is verifying X is in the language with the help of the certificate, right? So this is something that, again, this is where the non-determinism helps us. Okay, so now let us, using this, we will go on to the next characterization that I was referring to. That is, NP is a class of languages that have polynomial time verifiers. Right? So we already defined NP to be the class of languages that have non-deterministic polynomial time that can be decided by non-deterministic polynomial time Turing machines. Now I am giving another definition and saying that this is also a valid definition for NP. NP is a class of languages that have polynomial time verifiers. So I already defined what is a verifier. So now let me formally write it. So a language L is an NP if there exists a polynomial time verifier algorithm V such that, again now I'll just, such that X is an L if and only if there exists Y, and Y, the length of Y has to be polynomial in the length of X such that the verifier accepts X with the help of Y, right? This is the, so this is the formally, again this is the same definition that I made here, over here, but here it's more mathematical notation. There exists a polynomial time verifier algorithm V such that X is an L if and only if there is a certificate Y or a proof Y which is of short length, which is of polynomial length. So why do we want it to be polynomial length? Because if the certificate itself is too long, then the verifier is going to take too much time verifying this. So we want the verification process to be efficient, such that with the help of Y, the verifier machine V can verify that X is in the language. So if X is not in the language, there does not exist such a Y, which means for all the possible Y's that you can think of, right? So think about it, right? So what would be the negation of this? For all the possible Y, if X is not in the language, for all the possible Y, the verifier should not accept X, right? For all the Y's. Whereas if X is in the language, there need to exist only one Y. Right? There could be more, but there needs to exist only one Y. And what is P? Again, we already defined P, but just to contrast, we will write it in this form. P is the class of all languages that have a polynomial time decider. So in other words, let's say the decider algorithm is A. If X is in L, then A should accept X. Right? So which I write AX is equal to 1. So this is a simpler definition over here, but not NP is a slightly more involved definition. If X is in L, if and only if there is a verifier machine such that, and there is a certificate such that the verifier can accept X with the help of the certificate. Okay. So now we stated this definition that NP is a class of languages that have polynomial time verifiers, right? Now let's try to complete this proof. Let's try to complete this proof. There are two directions here. We have to show that NP, already the definition that we already saw, NP is a class of all languages that can be decided by non-deterministic polynomial time Turing machines. This means that the language has polynomial time verifiers. And second direction is that if it has polynomial time verifiers, then it is an NP. Okay. So suppose L is an NP. Okay. Suppose a language is an NP, which means there is an non-deterministic Turing machine that runs in polynomial time, say n power k time, that decides L, right? Which means we can look at the computation tree of the non-deterministic Turing machine running on X. Okay. So which means this is the starting configuration at the top, and then there is some tree. Suppose X is in the language, then we must be able to trace out a path that leads to an accepting state, right? So there could be multiple accepting states, there could be multiple rejects, but we should be able to find at least one path. Now, one way to make this into a verifier, guess and verify model is to give the identity of this path, right? So what is this path? So I first go left, then I go rightmost, then I go middle. So maybe I will say I can label the children of these configurations, and I will say first go the leftmost, then go rightmost, then go middle again, and so on till you reach the accepting path. So a non-deterministic Turing machine has the capability to identify an accepting computation path if it exists, whereas a deterministic verifier cannot do this. But if I tell you like you first go left, then go right, then go middle, then go right, whatever, then it is only the matter of verifying just one path from the root to the leaf, and this is easier to do, right? We don't need to traverse the entire graph, we just need to traverse one small path, the blue path that I have drawn in this figure. Hence it's easier to verify this. So what does a verifier machine do? On input y, input x and y. So what is y here, right? So y is we'll use another color. Y is the identity of the acceptance path of n on x. Okay. So what is it? So this is the certificate, right? So if x is in the language, there is some accepting path, and that accepting path is a certificate y, or the name of the accepting path, or the identity of the same, right? So what does the verifier machine do? It simulates n on input x, and when n has to make a non-deterministic choice, v will be guided by y. So basically it runs it runs as if n is running, but n makes non-deterministic choices. And what will we do? What will we do? We will follow the path as guided by the string y. Y will tell you which is the accepting path. So if there is an accepting path, y can encode that and we can verify that. If x is not in the language, all the paths will go to reject. So whatever y you give, we cannot be convinced to accept x, because the y's are all bad. All the y's lead to reject. And accept if n accepts, right? So now this is the one direction. The other direction is that if a language has a polynomial time verifier, then it is an NP. So suppose there is a language that has a polynomial time verifier. Okay, suppose L is a language that has a polynomial time verifier. let's say V is a verifier. Now assume that V runs in time n power k. Okay, so this means that now we need to come up with a non-deterministic Turing machine for the language, right? So what does we do? If a certificate is supplied, we will verify X with the help of the certificate Y, right? Now what does a non-deterministic Turing machine do? So non-deterministic Turing machine, what it does is it guesses a string y of length n power k, so as I have drawn here above. Basically the reason is, if the non-deterministic if the verifier runs in time n power k, then the certificate cannot be longer than that. So let the non-deterministic Turing machine guess a certificate of this length, right? And then run. So now it guesses a string of length y, right? So this process we have seen before. It can guess the first bit, then the second bit, and so on. Then run v. So now it has a certificate. Now you run v on the pair input and the certificate, right? And accept if and only if v accepts. So now the non-deterministic guess could be all the possible combinations of y's. If X is in the language, that X is a y that will lead to its verification, and hence that will correspond to a path in the non-deterministic Turing machine that will lead to an accept. If X is not in the language, there is no such y, and whatever path the non-deterministic Turing machine takes, it will lead to rejection. Hence we saw this. So if there is a non-deterministic Turing machine, polynomial time Turing machine that accepts the language, that decides the language, then the language has a polynomial time verifier, and if the language has a polynomial time verifier, then it can also be decided by the non-deterministic polynomial time Turing machine. So this is a alternate characterization or an alternate definition of the class NP. NP is a class of all languages that have polynomial time verifiers. So just to summarize, what are the proofs and certificates that we have seen so far? In the case of subset sum, it was the certificate was the subset itself that sums to the target sum T. In the case of CNF sat, it was the satisfying assignment of the Boolean formula, right? And in the case of three coloring, I'm not going to say it. You can think over it. What was the proof or certificate that the given graph is three colorable, right? So just to summarize, we have seen SAT and we have seen CNF SAT and pre-CNF SAT. Sorry. Then we saw the alternate characterization of NP, which is that it is a class of all languages that have polynomial time verifiers. And then we saw why this definition is equivalent to the previous definition, right? And now I just want to conclude, and before I conclude, I just want to say two small things. I believe I'll be able to share these notes with you, and you can read the proofs, detailed proofs, but I'll just share it. I'll just explain in brief now. Again, this is Theorem 7.11. These numbers are from CIPSR. I think the second edition is what I have, perhaps the third edition. In the time complexity chapter. What it says is that if there is a non-deterministic Turing machine that runs in Tn time, deciding a certain language, then there is an equivalent deterministic Turing machine that runs in exponential of Tn time, so 2 power order Tn time, that decides the same language. So equivalent means they both decide the same language. And if you recall the TOC proof that a non-deterministic Turing machine is equivalent to a deterministic Turing machine, this is kind of the same proof. What we do is, we simulate, basically the non-deterministic Turing machine has to decide if there is at least one accepting path, right? So, but then non-deterministic Turing machine can automatically kind of find the path if it exists. But deterministic Turing machine does not have the power to non-deterministically search for an accepting path. So it has to kind of do a depth first search or breadth first search in this graph, in the big configuration graph, right? So essentially that is the proof. So you want to search in this graph, so which is a usual traversal like depth first search or breadth first search. So what is the maximum number of configurations that can be there? That is the number of vertices in this graph or a tree. And to estimate the number of configurations, or to estimate an upper bound on the number of configurations, we make this assumption that, not an assumption, we assume that the maximum branching of at any configuration is some constant, and we call that constant b, right? So the maximum branching will be always limited by some number, right? Because it's just a function of the Turing machine, and so it will be a constant. So let's assume it is b, and once it is bounded, and it will be bounded for once the Turing machine is fixed, right? And it does not vary as per the input length. It's just fixed based on the Turing machine. Now at each, like let's say at level 1 there is one node, so level 0 there is one configuration, level 1 there could be at most b configurations, maybe not as much. Second level 2 there could be b squared, maybe not as much, and so on. So we have and the number of computation paths will be b power tn, where tn is the total number of steps required for the non-deterministic Turing machine. And using simple calculation we can see that the number of states in this graph is this one, b power tn into multiplied by tn, and we can see that this is upper bounded by 2 power order tn, which is a claim. So any non-deterministic Turing machine has an equivalent deterministic Turing machine with only an exponential, or with an exponential blow up in time. Maybe I shouldn't say only, because the blow up is huge, right? So if there is a non-deterministic Turing machine that runs in order n time, the corresponding equivalent Turing machine constructed using this procedure runs in 2 power order n time. So in specific cases you may be able to find simpler algorithms, but this is a general proof, and this gives you a general bound which is kind of very bad. And this part you can just read it out when I share the notes. All it's saying is that the branching factor, if it is large, we can replace it with a subtree of a branching factor at most 2, at the expense of the number of levels in the tree. You can just have a look. And that's it for this lecture. So just to summarize, we saw SAT, 3-SAT, CNF-SAT, the alternate characterization for NP, and 2 simple results which say that any non-deterministic Turing machine that runs in time Tn has a equivalent deterministic Turing machine that runs in 2 power order Tn time. Okay. In the next lecture we will see NP completeness. See you then. Thank you.